Hi everyone, before we jump into the notes, I want to talk about notation first. So you've been seeing in your notes and homework a lot, this, okay, which we call f prime of x. Okay, so as you know, f of x is just the name of our function. Okay, so f is the name of our function, x is our variable. Okay, it's just another way of representing the dependent variable y. Okay, these are essentially interchangeable. Okay, so f prime of x is just telling us the derivative. So this little tick here is not an exponent. It's telling us to take the first derivative. So this we call prime. So f prime of x. Okay, hypothetically, if we wanted to take the second derivative, which yes, you can take the derivative more than once, and we'll talk about that later. Okay, you would put two tick marks, right? F double prime of x, and so on. And we can talk about more of that later. Okay, so similarly, you might see y prime, which again, f of x and y are very similar, basically interchangeable. Okay, and the tick mark right there is just telling us to take the derivative. Okay, an alternate form of notation that you might see is d over dx. Okay, where this is basically telling us to take the derivative with respect to x. Okay, so this down here defines our variable. So you might see something like dy dx, okay, where y is our function. Okay, so that's our dependent variable. X is our variable. Okay, that's what we're taking the derivative with respect to. And you might also see like dy dt, okay, where t is our variable. So like we're dealing with a function with time or something like that. Okay, so all of these are just telling us to take the derivative. It's just different ways to say the same thing. Okay, so let's take a look at our notes. Okay, and so the first thing we're going to talk about is called power rule. Okay, and this makes taking the derivative of any polynomial especially really easy, but any x to some power. Okay, so again, this is just telling us to take the derivative with respect to x, which is our variable. Okay, and to do power rule, you take the exponent, you drop it to the front, x just chills, and then you subtract 1 from your exponent. All right, so let's practice. Here I have f of x, which is x cubed, and I want to find f prime of x. So I drop my exponent down, x chills, and then I subtract 1 from my exponent. So that means that the derivative is 3x squared. Right, same thing here, except I have a square root. That's the same thing as x to the 1/2 power. Right, so that 1/2 drops down to the front. I got x, and then I subtract 1, so I get negative 1/2 as my exponent. And you don't have to simplify, just leave it just like that. Right, here, let's write this in terms of an exponent. So I have t to the negative 4 power. Okay, so the negative 4 drops to the front, t chills, and I subtract 1, so negative 5. Okay, and same thing here. This we can think about as 5x to the 0 power, because x to the 0 is just 1. Okay, so this is a constant. And so if I take the derivative, I got 5, and this 0 is going to drop down to the front, and then I continue to do power rule. But it doesn't really matter what else is going on, because this 0 cancels everything out. So in the end, I just get 0. Okay, so the derivative of my constant was just 0. And that makes sense. If you think about the graph of the constant function, it has a slope of 0. Right, so the derivative, which again is basically slope, is just 0. That's what we're saying here. Okay, and again, the derivative with respect to x of 5x cubed. So if you already have a coefficient, that's just going to chill where it is, and then you multiply it by this derivative here. So 3x squared, okay, 5 times 3 is 15. So my end result is 15x squared. Okay, as we said from part D, the derivative of a constant is always going to be 0, okay, because the slope of any constant function is 0. All right, let's keep going. Sum and differences. So if I have two functions adding or subtracting together, and I want to find the derivative, you can just find the derivative of each part of your function independently. And all that means is that if you have a bunch of things adding together and you want to find the derivative of the whole thing, you can just find the derivative of each term one at a time. You don't have to think about it as a whole. You can think about it as a sum of its parts. So our first example, I have 4 terms all being added together, and I want to find the derivative. So I can just take the derivative one term at a time, right? So here I have 4 times, take the derivative of x cubed, so 3x squared, minus 5 times, take the derivative of x squared, which is 2x to the 1 power, plus 7 times, I drop my 1 down, right? So this is really x to the first power, so it's 1 x to the 0 power, and then I have the derivative of a constant, which is 0. All right, let's simplify this. I got 12x squared minus 10x plus 7. Right? And if you'll notice, I have 7x here, and the x kind of goes away in my answer. That's something that'll typically happen. That'll always happen because I end up getting x to the 0, and so that 0 will cancel out. Will just become 1, so it kind of goes away. Okay, in our next example, I see that I have 3 terms being divided by an x. Okay, so if you ever see this, where you just have your variable chilling by itself in the denominator, it's going to make your life a lot easier to divide each term by your variable, right? So I can divide everything by x. I'll get 5x to the 4th minus 3x cubed plus 4x to the negative 1 power. Okay, taking the derivative, again, one term at a time. Let's get some steps this time. So 4 times 5 is 20, x to the 3rd. Negative 3 times 3 is negative 9x squared. 4 times negative 1 is negative 4x to the negative 2nd power. Right? And again, you do not have to simplify, just leave it like that. Okay, I want to know where this function has a horizontal tangent line. If you think about what that means, like we said before, if you have a horizontal line, it has a slope of 0, which means that my derivative will be 0. So I want to know where the derivative of this function is equal to 0. Okay, that's what the question's really asking. So it'd probably be smart to find the derivative. So 3x squared minus 12. Okay, and I'm going to set this equal to 0. So let's solve. I get x squared is equal to 4. So x is plus or minus 2. Right, so at plus or minus 2, I will have a slope of 0, or I'll have a derivative of 0. So the tangent line will have a slope of 0, meaning that it is horizontal. Right, so that's what the question was asking. All right, moving on to some trig. The derivative of sine is cosine. The derivative of cosine is negative sine. Right, and if you take a look at the graphs, it kind of makes sense. Or if you think about the unit circle, it kind of makes sense because it's cyclical. One way to remember this is, if you remember, snow cone, snow cone. Yeah, that's what we say. The bottom two are negative, and you go down. Okay, so if you can remember this little mnemonic, the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine, and it just keeps going in a circle like that. Okay, so our sine cosine functions, the derivatives are cyclical. They'll just keep going. You can remember it this way, you can remember it whatever way you want. Let's try an example. So the derivative of 6x squared is going to be 12x, and I got 5 here just chilling. Now the derivative of cosine is negative sine. Okay, and so we'll end up with 12x minus 5 sine of x. That's a sine, I promise. Okay, a little review on average and instantaneous rate of change. We can call this AROC for short and IROC for short. The average rate of change is over an interval. Instantaneous is at 1 point. Right, so let's practice. I want to find the average rate of change between 1 and 5, so I need to find f of 5 minus f of 1 over 5 minus 1. And this is just slope. It's the it's the difference of my y's divided by the difference in my x's. That's just slope. You've been doing that for forever. Right, so we can plug in. So I have 5 cubed minus 3, 5 squared plus 4. Sorry, minus, I'll erase that. Okay, minus 1 cubed minus 3 times 1 squared plus 4. All that is being divided by 4. Alright, let's practice our mental math. We got 125 minus 75 plus 4 minus 1 plus 3 minus 4 all over 4 That does not look like a 4. Okay, minus 4. And because I'm so smart, I know that's 52 over 4, which is 13. Okay, so 13 is our average rate of change, meaning that is the slope of our function sort of on this interval between 1 and 5. All right, so remember this is a secant line. All right, so we just found the slope of our secant line between 1 and 5. Okay, now for instantaneous, I need to find the derivative. Okay, so remember that's a tangent. I need to find the derivative. So the derivative of f is going to be 3x squared minus 6x. And I need to find f prime of 3. So let's go ahead and plug in 3. So 3 times 3 squared minus 6 times 3, which is going to be 27 minus 18, or 9. Right, so 9 is the slope of my tangent at 3. 13 is the slope of my secant between 1 and 5. Okay, so this is over a period of time, say, between 1 and 5. 3 is instantaneous at one point in time. Okay, at one point. That's the difference. All right, last example. I want to find k so that my function is tangent to this line. Okay, and this is very important, this word right here. What two tangent functions tell me, or rather, if two functions are tangent, I know that they share the same slope and the same point. Okay, that's what I know. Okay, so what this is telling me is that because they have the same slope, I know that their derivatives must be equal. Okay, so the derivative of x must be equal to the derivative of y. I also know that they share the same point. That tells me that my function must be equal to my line. Okay, those are the two things that I know because they're tangent. All right, so let's set up some equations. First, let's set up our derivatives. So I know that f prime is going to be 2x plus k, because k is just a constant. And that has to be equal to the derivative of y, which is just 2. Okay, and I also know that my functions have to be equal. So x squared plus kx has to be equal to 2x minus 9. Okay, and this is good because I have two variables and I have two functions. Right, so if you have two variables, you need at least two functions to solve. So this is kind of like a piecewise function here, or it's a system. It's a system of functions, not a piecewise. We have a system, so you can use whatever method to solve a system. I think substitution is the easiest. So if I take my first equation and solve it for k, I get 2 minus 2x. And you might be thinking you might want that you would want to sub x out of my function to get k by itself, but it ends up being way easier if you solve for x first. So let's substitute k out of my equation, which is kind of counterintuitive, but it ends up working out. I get x squared plus 2 minus 2x times x equals 2x minus 9. Okay, all I did was I knew that k was equal to this right here, so I substituted that for my k value right here. Okay, I just substituted that out. Let's simplify. All right, these two x's will cancel, so I end up with negative x squared equals negative 9, meaning that x equals plus or minus 3. Okay, so I just skipped some algebraic steps there, but I end up with that x is plus or minus 3. Okay, now I don't care what x is, I care what k is. So let's plug back into my function here. So I know that k is going to be 2 minus 2 times positive 3, and k is also going to equal 2 minus 2 times negative 3. Right, so if we simplify this, I end up with negative 4, and I end up with 8. So k is going to equal negative 4 and 8. So this is my final answer. Okay, and so let's check that. Okay, so again, what this is saying is that if I plug these values in for k right here, that I should get two parabolas in this case that will be tangent to my linear function. Okay, so let's check that on a calculator. Oops. All right, I can go to my y equals, all right, and I plug these values in for k, and this is my linear function. And on my graph, there's my first parabola, there's my second parabola, and there's my line. And I see that it is indeed tangent, so it only touches each of these at one point, right? So it goes right along there. Right, that's it for these notes. I will see y'all later.